All right, the last section in chapter 13 is motion in 3 space. So in this section, there are some interesting application problems in physics. There's already a physical connection and interpretation to everything we've done, but in section 13.5, we really emphasize that physical connection. So just like in Calc 1, if r is position, so if r is position, then the first derivative of it, r prime, is velocity. And the second derivative of r, or the first derivative of v, is the acceleration. One thing that is useful that connects this section 13.5 back to section 12.3 with the dot product is the decomposition of the acceleration vector into the tangential and normal directions. So given some sort of path here, okay, so let's say this is the path traced by some r. At a certain point, let's say right here, we just talked about how there is a unit tangent vector. There is a unit normal vector. Oops, let's do this in blue. Trying to make them have the same length. Okay. And then we have an acceleration vector. So we know that the vector r prime is going to be in the same direction as the unit tangent. Now, it could be a lot smaller than t. It could be a lot bigger. It depends on what the actual speed is. This has length 1. So if your instantaneous speed at this moment in time is 20, then this vector has a length of 20. Not drawn to scale. And if your actual speed is like 0.5, then it's half of that. Okay, so r prime is in this direction. Now r double prime, on the other hand, this can be bending in different ways. Okay, that can change. It can be right in the middle, it can be this way, it can be this way. Kind of depends on the actual thing, on the actual parameterization. But what is useful is knowing how much of your acceleration vector is in these two directions. So for instance, let's go ahead and say that the acceleration vector is this green vector, and let's say it is something like let's say this is the acceleration vector. That seems plausible because at this moment in time we start curving downward. Okay, so that seems plausible. So what we want to do now is think about how many copies from this position right here, how many copies of this capital T vector do we need to add to how many copies of this capital N vector to sum to this A? Well, looks like we should have something. We should have this scaled amount here. And then we should also have a little bit more. All right? Those two vectors together should give us right there. So let's go ahead and draw that back a little bit differently. Let's put this right here. Oops. Let's move A. There we go. There we go. So this vector here is some number, let's say a sub n, times the normal vector. And this vector is some number, is some number of times, call it a sub t times t. So the acceleration vector A should be this number of times the tangent plus this number of times the normal. And if we add them together, we will get the acceleration vector. So these two numbers in boxes here, these are just the relative amounts. These are scalar factors. These are real numbers, but these are real numbers. Okay? So the way we can figure this out very easily is the easiest one to figure out is a sub t. A sub t, we can just go ahead and project the vector A onto the unit tangent. So project it. So remember that projection formula is, right? So if we have our acceleration vector A, and we have our unit tangent vector, capital T, if I project this down onto this vector, then we're going to get a vector like this. Okay, so that's A parallel to T. That is the proportion, it's the amount, it's some amount times T. What is this number here? This is A dot T divided by the length of T. Well, what's the length of T? I think I wanted to use this color instead. Whatever. Can I change that? That'd be cool. Oh yeah, cool. Okay. So, oh, squared. This should be squared in the bottom there. Well, what do we know about the capital T? Capital T is a unit vector. So that's 1. So then we have A dotted with T times T. So clearly, this right here is what A sub capital T is, because that's exactly what we defined this to be. Some real number times capital T. Well, here's some real number, because the dot product of two vectors is a real number. So there's our some number times capital T. So when we dot the unit tangent with A, this effectively extracts the relative amount, the scalar factor. It's the amount of A in the direction of T. And then you can very quickly get A sub n by doing some subtraction here. This is useful from a physical point of view, just to know how you're at this location here, depending on what your acceleration is, how much of it is pushing you this way, how much of it is pushing you this way. That can be useful.